AB Calculus, section 5.4, day number 2, the fundamental theorem of calculus, part 2. Our goal for today is to know and apply the second fundamental theorem of calculus. So we're going to talk today about FTC2. Okay, FTC1 says that if big F prime of x is equal to f of x, then the definite integral from a to b of little f of x with respect to x will be equal to big F at b minus big F at a. Okay, that is a big F. And that's going to be utilized today to formulate what's called the second part of the fundamental theorem of calculus. So let's get into example 1 and look at first the notation and determine what is going on here. Okay, so it looks like we want to take a derivative of a definite integral which has a variable as one of its limits. This is real funky and kind of probably looks very, very foreign and may confuse you, but let's walk through just the mechanics of the fundamental theorem of calculus part 1, and then we'll tag this derivative after we walk through the process of finding that antiderivative using FTC part 1. Okay, so let's find the antiderivative of t cubed plus 2t squared plus 4, and then we'll evaluate that from 1 to x. Okay, so let's look at that. The antiderivative of t cubed is t to the 4th over 4 plus, that would be 2t cubed over 3 plus 4t, and of course I don't need the constant plus c since this is a definite integral. So I'm going to work that from 1 to x. Now you could examine that, make sure your derivative is correct. I'll do that just so I don't make a mistake here. If I took the derivative of t to the 4th over 4, I would get 4t to the 3rd over 4, which would reduce to t cubed. This would give me 6t squared over 3, which is 2t squared. And of course, the derivative of 4t is 4. So I'm good on my antiderivative. Let's do the evaluation process of FTC. Now, note that I got to make these equivalent expressions, so I would put my dx notation here. Okay, that kind of tagging this along with it. Okay, my spacing is going to bother me, but that's okay. So let's evaluate the inner portion of this expression. Okay, and then we'll take the derivative after. Okay, so evaluating this, I would get x to the 4th over 4 plus 2x cubed over 3 plus 4x. Okay, so that would be equivalent to big F evaluated at x minus big F evaluated at 1. So let's plug 1 into all of these t values. So that would be 1/4 plus 2/3 plus, looks like a 4. Okay, let's do a little algebra and simplify this expression here. I'm going to do this mentally here. Actually, I'll do it to the side. That would be 3/12 plus 8/12 plus 48/12. Okay, cool. So that's going to be 59/12. I'll just make mental note, 59 over 12. Okay, so what we're going to do is we are then going to take the derivative of this expression, x to the 4th over 4 plus 2x cubed over 3 plus 4, 4x, and minus 59/12. Now, I did a lot of work to find that 59/12, but look what's about to happen. When I take the derivative of a constant, it's just going to disappear. And this is very interesting, but what does my inner expression turn into when I take the derivative? Well, I get x cubed plus 2x squared plus 4. Now, let's take a look at the original and see if we find any patterns. Oh my goodness, look at that. So essentially, in this case, not in every case, but essentially in this case, the constant made absolutely no difference with regards to the answer, right? Because I ended up just taking the derivative of that constant at the end when I evaluated, and it disappeared. So if you have a constant involved, know that that will likely come out to make no difference with regards to your answer. What happens and what matters is if you have a function as one of your limits of your integral. And in this case, it looks like we almost just did a substitution, right? And for t in all these cases. Oop, I didn't have to put it there because clearly that's a constant. So I inserted x into each of the independent variables in the integrand. This is called the integrand. Okay, let's look at a second example, and then we'll start to make a generalization here about any patterns. Okay, so this is the exact same problem, except we've changed this function on the upper limit. It's now x squared instead of x. So we've got the same antiderivative. So I'll have t to the fourth over 4 plus 2t cubed over 3 plus 4t. We're going to evaluate that from 1 to x squared. And then we're going to take its derivative after that. Better spacing. I like that. Okay, so let's go ahead and evaluate the inner portion, and then we'll take the derivative. So if I evaluate from 1 to x squared, that would be x squared to the fourth, which is going to be x to the eighth over 4. I don't know why I put that in parentheses, but I'll work it into the problem. Okay, I plug an x squared into t cubed. I get 2x to the sixth over 3 plus 4x squared. Okay, I'm going to minus, so that's f, big F of x squared, minus big F at 1. I already know what big F at 1 is. It's 59 twelfths. Thank you to whoever created these notes, so I didn't have to do more algebra. I could just use the same values there. Okay, so I'm going to take the derivative of the following expression. X to the eighth over 4 plus 2x to the sixth over 3 plus 4x squared and minus 59 twelfths. Clearly the 59 twelfths will drop off momentarily. Let's look at our answer here. Okay, we get, that would be 2x to the seventh plus 6x to the fifth. Oops, nope, I made a mistake there. That would be 6 times 2, which is 12. 12 divided by 3 is 4, so it would be 4x to the fifth plus 8x. Okay, so there's our answer. Now, this is really interesting, but check out what I'm about to do, and you wouldn't necessarily see this, but I'm going to factor out a 2x. Okay, I'm going to factor out a 2x, and you'll see what happens here. If I take a 2x out of every term, look at what happens. I'm going to get x to the sixth plus 2x to the fourth plus 4. Okay, you're looking at me going, okay, well, does that make any difference? Well, just check this out. Okay, now what I'm going to do is I'm going to rewrite the following expression on the inner portion in the following way. Just like that. Now take a look at this. Okay, let's analyze this for a moment. So if you look at what we did in the previous example, right? We took x and we inserted it for t. Okay. In this example, essentially what we're doing is we are inserting x squared into t cubed and t squared. right? This is x squared inserted into t cubed, x squared inserted into t squared. However, there's this 2x thing dangling on the outside here, which is really interesting. Like, where does that come from? And why didn't it show up here? Well, it did. It just showed up as a 1. Right, so what does this 1 represent? This was the derivative with respect to x of that function, right? That thing that we saw up in the upper limit of the integral. That thing that landed right about here. We inserted it into the integrand for t, and then we multiplied by its derivative. Let's see if that holds here. Well, we inserted x squared into t in the integrand, and then we multiplied by, well, that's the derivative of x squared with respect to x. Very interesting. So let's make a quick generalization. The derivative with respect to x of the integral from a constant, let's say a, to some function f of x of some other function, let's call it h of t dt. Okay, now let's talk a little bit of detail about this. This is a dummy variable t. It's just a variable that sits there to take place because I can't have it be x, because this function can't be f of x and this function f of x. So don't really worry about the reasoning as to why this is t and not x. Just know that this variable has to be different. So it could be any variable. It could be theta, it could be y, it could be whatever we want it to be. It just has to be a different variable than the function given here. Okay, so really this is the general case of what we just looked at. Right? I don't have a specific function here in the integrand. So what we can do to generalize is that the derivative of an integral, okay, will end up following this pattern. We will take the function f of x, insert it into h, and then multiply by the derivative of the inner function. It's pretty much a comparison with the chain rule, right? You're inserting it and then you're multiplying by its derivative. So in that way, this pattern will hold true, and we don't have to integrate and then differentiate. It's a very interesting concept, and that is FTC Part 2. Okay. Now, we're going to see some complex situations here with derivatives that are going to require some extra work, but that's the general formatting of how you'll use the fundamental theorem Part 2. All right, let's look at a few examples. Okay, example 3, find the derivative of the integral from 1 to x of e to the t cosine of t. Okay, so using that pattern that I'd shown you above, that template, if you will, we're just going to insert x and then multiply by the derivative of x with respect to x. Okay, clearly that's going to be a 1. So the answer to this would be e to the x cosine x, and you'd be done. Okay, let's look at example 4. Okay, we're going to, again, we got a constant in the lower limit, so that will make no difference with regards to the derivative, as the derivative of a constant will just be 0. And therefore, we would get x cubed inserted into the function given. So that'll be x cubed squared plus x cubed, of course, then times the derivative with respect to x of x cubed. Okay, so if I clean that up just a little bit here, we would get 3x squared over the square root of x to the 6th plus x cubed. There's your answer. Very nice. Let's continue with a few more examples. Okay, now let's look at the formal definition here of the fundamental theorem of calculus part 2. It says if f is continuous, that is a requirement for this to hold on a closed interval a to b, then the area function is given. The area function a of x is just the integral from little a up to x of f of t dt. Notice the variable difference between this function and the function in the integrand. For a to x, for x between a and b inclusive, is continuous on a to b and differentiable on a to b. So this is continuous on a to b and differentiable on a to b. The area function satisfies a prime equals f of x, or equivalently, what we just talked about on the last slide. Okay? This means that the area function of f is an antiderivative of f on a to b. All right, so that's formal definition of what we just talked about on the previous slide. Let's look at example 5 and 6. Example 5, very similar to those that we saw on the previous page. So let's insert the upper function using our FTC part 2 shortcut and multiply by the derivative of that upper limit, which will be negative sine x. So our answer comes out to be negative sine x times sine of cosine of x. Very nice. Okay, take a look at this example 6. Okay, this is going to be interesting as we've kind of flipped it on you a little bit. Now my dummy variable is a u, as well as I've got a function in the lower and the upper limit. Okay, so let's walk through this. Okay, so let's take the long way here, and then we'll talk through the shortcut if you've got a function on the upper and lower limit. Okay, so I'm going to take the derivative with respect to x of the antiderivative of u squared, right? Evaluated from sine x to cosine x. So that'd be u cubed over 3, evaluated from, like I said, sine x to cosine x. And we'll generalize this, okay? So that'll be the derivative with respect to x of, it would be cosine cubed x over 3 minus sine cubed x over 3. Okay, so big F at cosine of x minus big F at sine x. Okay, that's just FTC part 1. Okay, now I'm going to take the derivative of that. That will be 3 cosine squared x over 3, which will be cosine squared x, okay, times, okay, so I got to multiply by the derivative of cosine then, using the chain rule, which is negative sine x, okay, minus 3 sine squared x over 3 times the derivative of sine x, which will be sine squared x times cosine x. Okay, so using the chain rule, I get that. Now let's examine what's going on here. Okay, this will be negative sine x cosine squared x minus cosine x sine squared x. So what I've done is, if I look at, and I look for kind of a generalization or a shortcut, if you will, what I'm doing is if I've got a function on the lower and upper limit, I plug in the upper function, cosine squared, multiplied by its derivative, negative sine, minus using FTC. Right? Now, before we had a constant here. So when we subtracted the constant and then took its derivative, it just disappeared. But in this case, when we subtract a function, right, and we take its derivative, we're going to be doing essentially the same thing we did with the upper function. So we plug in sine x, get sine squared x, and then we multiply by its derivative, which was cosine. And this minus right here comes directly from FTC part 1. So let me lay this out in a general form, and then you can use that general form continuing on with other problems. So if I take the derivative with respect to x of the integral from, let's go f of x to g of x of h of t dt. Okay, so this is just adding that lower function on the lower limit of the integral. Okay, what I would have is I'd have h of g of x times g prime of x. Okay, here's h of g of x, here's g prime of x, minus h of f of x times f prime of x. And that'll be FTC part 2 for a scenario that follows suit like this. So here would be h of f of x, and here is f prime of x. And you can see that from FTC part 1, that's where the negative or the minus in between comes from. Okay, don't memorize this stuff, guys. Don't memorize that, and don't memorize this, right? This is the same scenario, just a different different limits, but don't memorize these. Just do enough repetition that, oops, that should be next, that you get used to it and you figure it out. These are the fundamental theorem of calculus part 2. So let's do a few more examples, and then we'll continue on to some homework problems. Okay, I'm not gonna cover this slide with verbal explanation, but as you work through it and you look at each of these properties, try to make sense of it graphically. Okay, some of them are really basic and simple. I think I might, yeah, I will. I'm gonna go over just a couple of them. One, I'm gonna look at this. And then I want to look at even odd here down at the bottom, 11 and 12. So let's look at number 4, 11 and 12. You can look at 1 through 3 and 5 through 10 and just kind of make sense of some of these properties. And these properties, honestly, some of them are common sense, like number 5. Number 5 is just, I'll talk about that one too. That one's common sense. But let's look at number 4. Look at the rest and ask questions of your teacher when you're in class. Okay, number 4, that's telling us, for example, let's look at this integral here on the left side. The integral of f of x from a to b. Okay, so let's say this is f of x. Okay, and let's go from let's go a to b. Okay, so that integral from a to b of f of x would represent this area. Okay, cool. Now that's going to be equivalent to the opposite of the integral from b to a. So just understand that when you flip the limits, you change the sign of the area. Okay, pretty basic there. How about number 5? Number 5 here is a function, f of x. I want the integral from a to a of f of x dx. Well, the width of that space, that area, there is no interval, right? And therefore there is no area. So that's number 5. Let's go number 11. Let's take an even function. Even function like, let's go, how about x squared plus c? X squared plus c. My handwriting just failed me there. All right, if I integrate from negative a to a, right, that would be this area here. Notice how the symmetry of this graph would have us with 2 equal areas on both sides of that y-axis, and therefore that is why the integral from negative a to a of f of x is equal to 2 times the integral from 0 to a of f of x. So that's telling me that, this, which is the green and the yellow, is the same as 2 times the yellow. Right? Makes sense. With an odd function, very similar. Let's take sine. What's sine x? Okay. So this area here, I believe you would agree, would be symmetrical or equal in measure to that area there. Therefore, the integral from, let's go negative pi to pi, which would be these values, negative pi to pi, of sine x dx would be equal to 0, right? Because the red space would be equal in measure to the green space, except to have a negative value. Therefore, this would be true symmetrically about the origin. Any odd function, if you find the area trapped beneath the curve and the x-axis, or between the curve and the x-axis, will equal 0. So that's the odd property. Even property, I don't really have a name for this property, but you can come up with whatever name you want. And then, of course, this would be, if you're flipping the limits of the integrals, that's the property you would come up with. All right, let's continue. Okay, got a couple of non-calculator situations here. 98 and 2003. So let's go ahead and look at the following. It gives us big F of x, and it equals the integral from 0 to x of the square root of t cubed plus 1 dt. And it asks for the derivative of f at 2. Okay, so first I'm going to find f prime of x. Well, f prime of x, this is FTC part 2, right? Because if you have an integral and you're going to take its derivative, then you use FTC part 2. Now I see a constant in the lower limit, that's good. And I see a function, which is x in the upper limit, that's good. So I'm going to insert x, which will make this x cubed plus 1. And I'm going to multiply by the derivative of x, which is 1. So there's f prime at x. F prime at 2 will be the same with a 2 inserted in for x. Looks like that would be the square root of 9, which comes out to be 3. All right, there we go. So f, big F prime at 2 is equal to 3. All right, let's look at number 23 from 2003. Okay, very similar. You can see this is FTC2, just in a different form. Now they're not giving us a function as an integral and asking us for the derivative. They're giving us the Leibniz notation, which also signifies find the derivative. Okay, so now I've got constant lower, that's good. Function upper, that's good. I'm going to insert, so that would be sine of x squared cubed times the derivative of x squared, which will be 2x, which will give me sine of x to the 6th times 2x. Let's see if we can find that. Yep, looks like E. Okay, FTC part 2, get some reps in, you'll get better at it. Let's continue. Okay, number 92, also from 2003, this is in the calculator allowed portion. Okay, so before I get into the calculator, what I want to do is I want to analyze what the question is asking. Okay, so let g be a function given by g of x is the integral from 0 to x of sine of t squared between -1 and 3 inclusive. On which of the following intervals is g decreasing? Well, we know that g is decreasing. Okay, g will be decreasing when g prime is less than 0. That means I have to find g prime. Well, to find g prime, I got to use FTC part 2. G prime is going to end up being sine of x squared times the derivative of x, which is 1. So again, I see my lower limit is a constant, my upper limit is x. So there's g prime. So now what you're going to do is in your calculator, you're going to type in sine of x squared in for y1. And what we want to do on our graph is find where y1 is, whoops, I want decreasing. I want to know where g is decreasing, therefore I want to know where y1 is less than 0. That signifies that g prime of x is less than 0, which we know tells us a lot about what's happening with g. Okay, so take out your calculator, identify an interval, and then we can look at the answer. Okay, so I'm going to sketch out my graph here, and it's not going to be perfect, but here's my graph of y1, which equals g prime of x. Okay, and I got one of those newer calculators, so I'll go blue. Now, what I did with my window is I went from -1 to 1 here for my y values, and I went out to 3 for my x values, and that just gave me, of course, and actually, I'm sorry, I went out -1 as well here to match this interval here. Now, why did I go -1 to 1 on the y values? Just because all I want to know is where g prime is less than 0. I don't care if it goes way up here. I just want to know where it intersects the x-axis. Okay, so when I graph g prime, it looks kind of like, I'm probably going to butcher this a little bit. It looks kind of like that. I mean, it's not perfect. But when I analyze and I take a look, I found that this point right here was the point x equals 1.772. And this point here came out to be x equals 2.507. So the interval in between, right, is where g prime of x is less than 0. That tells me that g of x is decreasing. Thus, I can say with confidence that on that interval given in part D, g prime is less than 0, thus g is decreasing. All right, let's continue with a non-calculator from 08. Okay, here, the graph of f is shown above. It has horizontal tangent lines at x equals 2 and 5. Okay, so that means that I know here f prime at 2 is equal to 0 and f prime at 5 is equal to 0, just to take that information and to think about it a little bit. Okay, let g be the function given by the integral from 0 to x of f of t dt. For what values of x does the graph of g have a point of inflection? Now this is getting a little messy, right? Okay, so let's just talk about this generally. G has a point of inflection if the following is true. G double prime is either equal to 0 or doesn't exist and changes sign. Okay, so we need to find G double prime. Okay, so let's go here and let's figure out how we're going to find G double prime. Okay, so we're going to use FTC part 2. I'm going to find G prime of x. Okay, looking at this, I've got a constant here, I've got a function here. It looks like G prime of x is just going to equal f of x. Okay, I insert x in for t and multiply by the derivative of x, which is just 1. So now I've got this. Well, this is pretty easy to work with because now G double prime is just going to equal f prime. So as I look at the information that I have up here, G has a point of inflection if G double prime equals 0 or doesn't exist and also changes sign. That means I could actually, because G double prime is equal to f prime, I could substitute in or think of this as f prime. So I'm looking for f prime. This is kind of informal, but where is f prime of x equal to 0 or doesn't exist and changes sign? Okay, so let's analyze this graph. Notice that f is increasing and then decreasing, and it changes from increasing to decreasing at x equals 2. That means f prime, as we noted here, is equal to 0 when x equals 2. Same happens when x equals 5, other than the fact that the function f is decreasing, then increasing. So I can say that f prime is 0 and changes sign at x equals 2 and x equals 5. Now I don't have to worry about is f prime ever not exist. It doesn't show up in this graph. This graph is continuous and differentiable, and therefore I won't run into that issue. But I can say with confidence that since f prime equals 0 and changes sign at 2 and 5, that means that G has a point of inflection at both x equals 2 and x equals 5. All right, let's continue with a few more examples. All right, let's look at the next example here. Looks like an example from 2012, number 3, non-calculator. Okay, so the first thing I want to draw your attention to here is that we do have a graph of f of x, right, and it's made up of these line segments and a half circle, as well as this line segment here. It says f is continuous on the defined, on the interval -4 to 3, whose graph consists of these 3 line segments and a semicircle centered at the origin. Let g of x be this function here, given by the integral from 1 to x of f of t. Okay, so that right there is absolutely 100% screaming at you FTC number 2. Right? It's likely that we're going to have to use FTC part 2 for that, involving that equation. Okay, so let's look at what part A is asking us. Part A says find g of 2. Well, by definition, g of 2 will be the area from 1 to 2 trapped between f of t and the t-axis. Okay, so let's take a quick look at what that would look like. That's the area between the curve. Looks like a small triangle here. All right, so it would be that area there, which of course we can calculate. You can see that the base length, right, from here to here, we could call that the base, that would be 1. The height would be a negative 1/2. You can see how the slope of this line goes over 2 and down 1. So it's a slope of negative 1/2. Therefore, this height here, change in x, change in y would be negative 1/2. Thus, this area would be half base height. So it looks like g of 2 is negative 1/4. All right, let's look at g of negative 2. G of negative 2 will be the integral from 1 to negative 2. That should start to sound some alarms in your head of f of t dt. All right, anytime that I see the limits on my integral from greatest to least, right? Your greater number is in the lower limit, your lesser number is in the upper limit. What I do is I switch them, right? When I switch those limits, what happens is the sign of the area becomes the opposite. So that's why I put that negative in there. Okay, now why would I do that? Because we integrate from left to right. From left to right. So hang on to this negative here, and I'm going to find the area beneath the curve from negative 2 up to 1. So that's going to include everything here and this half circle here. So this area will come out to be the opposite of whatever the area in green is there. Okay, so let's analyze this. Got a triangle here, base of 1, height of 3. Therefore, that triangle's area would be a positive 3/2. And the area trapped beneath the t-axis between this circle and the t-axis from negative 1 to 1 is going to be clearly a negative area, right, because it's beneath the t-axis. And we're going to take the area of a circle with a radius of 1. So here's the radius of 1 and the area of the circle. And we're going to divide that by 2. So we're going to get a negative pi over 2. Thus, when I distribute the negative, I would get a positive pi minus 3 over 2. Okay, so this will come out to be a positive number, which tells me that this area here, this triangular space, is a little bit bigger, right, than this half circle here, or semicircle. Okay, so that's part A. We got g of 2. G of 2 ends up being negative 1/4, and we got g of negative 2, which is pi minus 3 over 2. Okay, let's take a look at part B. I'm actually gonna, can't erase that. That's cool. Thanks for that. All right, I guess explain everything isn't as awesome as I thought. Part B says find, or for each g prime at negative 3 and g double prime at negative 3, find the value or state that it does not exist. Okay, so first I got to find g prime. Well, g prime of x using FTC part 2 is going to equal f of x. So g prime at negative 3 is actually going to equal the output of f at negative 3. Let's take a look and see what that'll be. F at negative 3, based on this linear function here, looks like it will be 2. So g prime at negative 3 is a positive 2. How about g double prime? Well, if g prime of x is f of x, then g double prime of x would be f prime of x. Okay, thus g double prime at negative 3 is actually going to be the slope of f at negative 3. So if I were to look at the slope of this line, that would represent the slope of the tangent line of f at x equals -3, which I believe comes out to be 1. Okay, so there's A and B. I would say if you're going to allocate markings here, or points, I'd say A is probably worth 2, and B is probably worth 2, maybe 3. So you're looking at, if you can get through those unscathed, you're looking at probably 4 points out of the 9 for this FRQ, which is pretty good. Okay, let's look at part C. Part C says find the x-coordinate of each point at which the graph of G has a horizontal tangent line. So if G of x has a horizontal tangent line, horizontal tangent line, abbreviations here, when G prime of x equals 0. Well, I know that G prime of x is equivalent to f of x, and therefore I can say, based on my graph, analyzing this, well, f of x equals 0 at -1 and +1. Therefore, I can say G of x has a horizontal tangent line at x equals -1 and x equals +1. All right, now let's go further with our analysis and determine whether G has a relative min, a relative max, or neither at those points. Okay, so let's talk about relative min, relative max. G of x has a relative max when G prime changes sign from positive to negative. All right, so let's analyze our two locations. In this case, we're looking for when, not G prime on the graph, but we're looking for where f of x changes sign from positive to negative. Okay, so f of x, positive, 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 at -1 changes from positive to negative. Therefore, G of x has a relative max at x equals -1. Let's look at the other. Well, we'll notice that f of x is less than 0, then 0, then less than 0 again. So f of x does not change sign at x equals +1. Therefore, we could talk about what defines a relative minimum. It'd be very similar to this statement here, but we can say that G of x does not have neither or either, I don't know, but G of x does not have either a relative max or relative min at x equals 1. So it's got neither at x equals 1. Okay, so we've justified our answers. I would say, as you look at part C, right, we've stated, right, that G has a relative max at x equals -1. That's your answer. Your justification for that is everything that we wrote here. So this wasn't just for explanation purposes, it was also for justification. All right, and I guess we should put a justification here, but we could say G of x does not have either relative min or relative max at x equals 1. That's our answer, and our justification is because, let's say, G prime of x, which is equal to f of x, does not change sign at x equals 1. Okay, let's dig into part D. Okay, part D says find all values of x for which the graph of G has a point of inflection. So we got to go back to our FTC here again, right? And when we went back to our FTC, we could see, FTC part 2 that is, we could see that G double prime is equal to f prime. Okay, so I'm going to try to do this without losing my graph. Okay, I'm pretty good there. All right, part D. We know that g of x has a point of inflection if g double prime of x changes sign. Now, recall that this could happen anywhere that g double prime, right, equals 0. So we could have its sign change when g double prime equals 0, or when g double prime does not exist. Right, so we got to be aware of that. And that actually could have happened also for part C with relative min, relative max, but the problem prompted us, right, with these horizontal tangent lines. Okay, so as we look at the rest of this, let's talk about how we're going to analyze the graph of f prime when looking for g double prime's sign change. So I'm going to look at the slope of the graph above, and when I look at the slope of f, that's going to indicate the values of g double prime. So I want to know where g double prime changes sign from positive to negative or negative to positive. Does not matter, right? We don't have to get specific about which it changes from and which it goes to, because points of inflection we don't classify based on that, like we do relative min, relative max. Okay, so let's look at the graph, and let's look at when the slope of f changes sign. So f prime positive, right? I got a positive slope here, and then we change sign to negative. Well, f prime doesn't exist here at x equals negative 2. That meets this characteristic, right? G double prime does not exist because f prime does not exist at negative 2, and f prime changes sign. So I'm going to say that g of x has a point of inflection at, we're going to start with x equals negative 2. Let's see if there are others. Okay, it looks like g double prime or f prime does not exist here at x equals negative 1, but we don't change sign because f prime is negative and then does not exist and is still negative. So we got to be careful there. That is not a point of inflection at x equals negative 1. Okay, so f prime, slope of f is negative, 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 0. Right, so here f prime is 0, which means g double prime is 0. And we change from f prime being negative to f prime being positive. So there's a point of inflection at x equals 0. Let's see if there's any more. F prime is positive here, which means g double prime is positive. Here f prime doesn't exist, therefore g double prime doesn't exist. And then f prime takes on a negative value. So we go from f prime being positive to not existing to negative. That tells us that g double prime is positive, doesn't exist, to negative. Therefore, there is also a point of inflection at x equals 1. All right, guys, that's a pretty in-depth look at this FRQ. Talk with your teacher if you got any questions. Let's move on to our last example for the day. Okay, it looks like we got a calculator aloud question here from 2006, problem number 3. So let's just go ahead and jump into it. It gives us the graph of f shown above, consisting of 6 line segments. Let g be the function, which is the integral from 0 to x of f of t dt. This is FTC part 2, screaming right off the page. Okay, part A says find g of 4. G of 4 is going to be the integral from 0 to 4 of f of t dt. So I want the area under the curve from 0 to 4. Okay, that's going to be, right, we're gonna look at these areas. It's going to be this little triangular space, which will be negative in area. Okay, so that little triangular space is going to equal 1/2 the base, which is a length of 1, times the height, which is a length of negative 2. Okay, plus, then I'm going to find this trapezoidal space right here. Right? Okay, it's got a height of 2. It's got a base length of 3 and 1. So I'm going to take and add 1/2 base lengths of 1 and 3 and a height of 2. So g of 4, geometrically, I can do this, is -1. I'm telling myself I can do this, plus 4. So g of 4 should be 3. Okay. If you want to think of it this way, like you could see this as like, because of the linear nature of this portion of the graph, like this part of the graph here is going to negate this part of the graph here, so they'll cancel out, and then I'll get, you know, this rectangle, which is a 1 by 2, which is 2 units, and then this, which is 1 unit, which makes 3. All right, however you want to go about that, that's fine. All right, let's find g prime at 4. Before we find g prime at 4, we got to find g prime of x. Well, g prime of x using FTC is going to be f of x. Okay, that's FTC part 2. Okay, so g prime at 4 is going to be equal to f at 4. So very simple. Look at your graph. What is f at 4? F at 4 is 0. All right, just analyze your graph, guys, right here. F at 4 is 0. Okay, g double prime at 4. Well, g double prime of x is related to g prime of x. Thus, double prime at x will be equivalent to f prime at x. So g double prime at 4 is going to be equivalent to f prime at 4, which is the slope of f at x equals 4. So if I look at this segment here, looks like I'd go down 4 units over 2 units. So the slope of that portion of the curve would be a -2. Okay, that's part A. Part B, does g have a relative min, relative max, or neither at x equals 1? Okay, so when we talk relative min, relative max, we're talking about g prime, right? So if I'm considering the function g, I want to analyze g prime. Okay, so I know g prime of x should equal 0 at x equals 1, if any of this is to even be possible. So let's make sure that that's true. So g prime of x is equal to f of x. Is f of x equal to 0 at x equals 1? The answer to that is yes. Okay, so at least we're in the neighborhood here. Okay, so we know that we can figure here what's happening. Okay, so f of x represents g prime of x. So f of x is less than 0, then 0, then greater than 0. That means that g prime is negative, then 0, then positive, which means that g will have a local minimum at x equals 1, because g prime of x, which is equal to f of x, changes sign from negative to positive. Okay, that'll do for part B. Let's look at C. Suppose that f is defined for all real numbers x and is periodic with a period length of 5. The graph above shows 2 periods of f. Okay, so you can consider, like, here's one period. Periodic just means it repeats the same pattern. Okay, here's a second period. Okay, given that g of 5 is 2, okay, given that g of 5 is 2, find g of 10 and write an equation for the line tangent to the graph of g at x equals 108. Okay, so let's take a look at and determine how we're going to do this. Now, the fact that g is periodic, f is periodic with a length of 5 means something very interesting here in this case. So let's look at this. So given that g of 5 is 2, okay, so my second periodic, my blue periodic portion here, right, it's going to look like this. It's not perfect, but it'll do. Okay, so let me scratch away some of this. There we go. So what we're saying here is that g of 5 is 2. What happens is this little space here and this little space here, They negate each other. Likewise, these two here. And the periodic nature of the function itself, you know, this space here is 2. So if g of 5 is 2, and I put another period of this same function up here, right, which is just the area beneath the curve, you're going to see the same thing happen. You'll see the red and the green, right, and they'll all just kind of reduce out. And so, you know, g of 10, which they're asking us for here, will be 2 2's, which will be 4. Okay, it says find g of 10. Well, we just found it, right? It's double that, right? Because of the red and the green negating, and then the summation of the white space, which is 2 units each. It says write an equation for the line tangent to the graph of g at x equals 108. Anytime you want a tangent line, okay, we need a point, we need a slope. So let's talk about a tangent to g. Okay, so I want to know g prime at 108, and I need to know g at 108. Well, g at 108 is going to be equivalent to the integral from 0 to 108 of f of t. Now, in finding this, I can utilize this idea. Okay, so how many times does 5 go into 108? I think it's 108. Yeah, it's 108. Well, 5 goes into 108. It looks like 21 times with a remainder of 3/5. So there'd be 21 of these. Okay, so that'd be, let's see, 21 2's. Oops, 21 2's plus 3/5 of one of those intervals, right? 3/5 of one of those periodic. Okay, so 3/5, right? This was x equals 1, this is x equals 2, this is x equals 3, this is x equals 4, this is x equals 5. So if I just have 3/5 of one of those, right, I'm kind of left with this here. Well, that's still just going to be 2. So then I'm just going to add on an extra 2. So g of 108 is just going to be 44. So I have 21 periods of f plus 3/5 of a period, which adds up to 44 units or square units. Now g prime at 108 is going to be the same as f at 108. So that's interesting too, right? Since this function is periodic, I can take 108, again, divide by 5. What does that give me? That gives me 21 and 3/5 left over. So at 3/5, really it's going to act the same. The function will act the same as it would at x equals 3. So that means that f at 3 is going to be the same as f at 8. It's going to be the same as ... all the way down the line, f at 108. And there you have it. So f at 108 is the same as f at 3, and f at 3, I believe, ended up being 2. So we get a 2. Now we can write the tangent to g at 108. That would be y minus, it looks like 44, is equal to g prime at 108, which is 2, times x minus 108. Okay, recall this is the point 108, comma 44, and of course this is our slope. Okay guys, that's it for this lesson. Kind of a doozy, lots of work there, but we will see you in the next video.